In this video, we're going to look at sketching an antiderivative given a derivative graph. So here we're given a graph of the derivative f prime of x and capital F of 0 is equal to 50. The question here is to sketch the graph of the antiderivative, where capital F of x is capital F of 0 plus integral from 0 to x f prime of t dt. That's just an application of the fundamental theorem of calculus. So from the graph, you can see that the derivative graph is piecewise continuous. We do have a jump discontinuity at x equals 20 and also at x equals 30. But this function, this derivative graph, is piecewise continuous on the entire interval from 0 to 40. All right, so the solution here is capital F of x is equal to f of 0 plus integral from 0 to x f prime of t dt, and that's just the application of the fundamental theorem of calculus. How do we find the critical points of capital F of x? These actually occur at x equals 20 and x equals 30. And from the graph, you can see how the derivative graph cuts through the x-axis at x equals 20 and also at x equals 30. So we expect to have maximum or minimum for the antiderivative. So capital F prime of x is equal to d dx integral from 0 to x f prime of t dt. That's equal to f prime of x. Derivative cancels the integral out, and we just get f prime of x. So capital F prime of x is equal to 0 when small f prime of x is equal to 0. That means where f prime of x cuts through the x-axis, we will have maximum or minimum for capital F of x. Looking back at the previous page, you can see at x equals 20, the derivative is going from positive to negative, so we expect to have a maximum for the antiderivative. And similarly, the derivative graph is going from negative to positive at x equals 30, so we expect to have a minimum for the antiderivative, capital F of x. What about the inflection points? Inflection points of capital F of x occur at x equals 10 and x equals 25, where f prime of x has a maximum or minimum. So looking at the graph of the derivative, you can see how at x equals 10, the derivative graph has a maximum at x equals 10, and minimum at x equals 25. And that's where we're going to have inflection points for the antiderivative. All right, so let's apply the fundamental theorem of calculus to do this sketch. The integral from a to b f prime of x dx is equal to capital F of x. Capital F of x is the antiderivative of small f prime of x, and evaluated from a to b. That's going to be capital F of b minus capital F of a. So fundamental theorem of calculus tells us that capital F of b is equal to capital F of a plus integral a to b f prime of x dx. All right, let's now apply that. We know that f of 0 is equal to 50. That was given in the question. F of 10 is going to be f of 0 plus integral from 0 to 10 f prime of x dx. Capital F of 0 is just 50 plus 1/2 of base, that's 10. The height is also 10. Let's go back to the graph. So we can see that 1/2 the base, 1/2 of from 0 to 10, that's 10. And then the height is also 10. So half the area of the base times the height gives us 50. All right, so that's going to give us 100. Capital F of 20, that's going to be capital F of 10 plus integral from 10 to 20 f prime of x dx. Capital F of 10 is just the previous value, that's 100. The integral from 10 to 20 f prime of x dx is the area of this rectangle from here to here, from 10 to 20, and that's the area of this triangle is just going to be 1/2 the base times the height. So 1/2 of 10 times the height of 10, that's another 50. So let's add that. That's 100 plus 1/2 of 10, 1/2 the base times the height of 10, and that brings us to 150. F of 25, capital F of 25 will be f of 20 plus integral from 20 to 25 f prime of x dx. That's a capital F of 20 is a previous value, that's 150, plus the integral from 20 to 25 f prime of x dx. Now, from 20 to 25, you will see that the graph has dipped below the x-axis. That means we have to subtract off the area. So half the base, 1/2 of 5, times the height of 5, that's going to be 1/2 of 5 times 5, that's 1/2 of 25. I guess that's 12.5. We're going to subtract that. All right, so what we have is f of 25 is f of 20 plus integral from 20 to 25, f prime of x dx. And we're going to subtract off, so let's subtract that. That's minus 1/2 times 5 times 5. And that gives us 137.5. All right, now let's look at f of 30. F of 30 is going to be capital F of 25 plus integral from 25 to 30 f prime of x dx. F of 25, that's just going to be what we had before, that's 137.5 plus, and now if you look at the diagram from 25 to 30, you can see that we're just going to, the integral represents the area of a triangle, and since the derivative graph is below the x-axis, we have to subtract off the area just like we did previously. So 1/2 of 5 times 5, we're going to subtract off another 12.5. All right, so that's going to be subtract minus 12.5, and that brings us to 125. Now let's look at f of 40. F of 40 will be capital F of 30 plus integral from 30 to 40 f prime of x dx. Capital F of 30 is 125 plus, what about the area from 30 to 40? How do we calculate this integral? Let's go to the diagram. You can see from 30 to 40, we just have a rectangle, so the area will be 1/2 the base times the height. The base goes from 30 to 40, so the base is 10 units, and the height is 5 units, so this area will just be 10 times 5 is 50 is the area of the rectangle. We're going to add that. So plus 10 times 5, that's 50, and we add it up, we get 175. All right, so now let's look at the graphing the antiderivative. So here we have both graphs. We have the derivative graph and we also have the antiderivative graph. You will notice something. Capital F of 0 is going to be 50. That's our starting point. And you can see how the derivative graph is increasing at an increasing rate. So the derivative graph is increasing. That means the capital F of x is increasing at an increasing rate. And that's what's happening here. And that means capital F of x is concave up. Now, from 10 to 20, you can see how the derivative graph is increasing, or decreasing, I should say. And that causes the antiderivative graph to be increasing at a decreasing rate. And now we get to x equals 20, where the derivative graph cuts through the x-axis, and we're going to have our local maximum for the antiderivative. Now, what's happening from 20 to 25? You can see how the derivative graph is decreasing. That means the antiderivative graph, capital F of x, is going to be decreasing at a decreasing rate. That means the antiderivative graph is concave down until it reaches this inflection point. Now, past 25, you can see how the derivative graph is increasing, and so that means the antiderivative graph is going to be decreasing at an increasing rate. So it will be concave up until it reaches the minimum point at x equals 30. And after that, you can see how the area function that we have drawn is a straight line. Why is it a straight line? The reason is because the derivative is constant. That means the antiderivative will be the antiderivative graph will be increasing at a constant rate, and that means a straight line with a constant slope. All right, so on the next page, we have review of the things that we did here. The theory, for example, capital F of x is equal to f of 0 plus integral from 0 to x, f prime of t dt. And we just kept applying this formula over and over again to sketch this antiderivative. And all right, thanks. I need to make a correction to this video. On the first page, I said that we have a jump discontinuity at x equals 20 and at x equals 30, but that's a mistake. We don't have a jump discontinuity at x equals 20. We only have a jump discontinuity at x equals 30 and also a jump discontinuity at x equals 40. So those are the only two places that we have jump discontinuities. This derivative graph is piecewise continuous on the closed interval 0 to 40. All right, thanks.